Yes, Assalamualaikum and good morning, everyone. Okay, so today will be our last lecture. So starting next week and week 14, we will have a presentation by uh, my colleagues, my friends, that will explain to you some of their research works uh, that use continuum solid mechanics or continuum mechanics in general. Okay, so before we can go into the talk and listen to their research work, um, I will explain a little bit about the last topic, which is related to the constitutive equations. Okay, so at the end of this lecture, you will be able to understand the linear elastic materials and also understand the hyperelastic materials. Okay, so last 2 weeks we have learned about um, the conservation laws that can be used to relate the stress and strain and the forces acting on the body. And then we also learned that to enable the uh, the constitutive law to be used, we need to have some relationship between the stress and strain, and that relationship uh, can is known as this constitutive equation. So constitutive equations are relations that connect the primary field, which is the displacement, velocity, and then strain, to the secondary field variables, which is the stress. So these equations are not derived from any physical principles, but they are derived to obtain certain rules or to obtain certain entropy inequality. So basically, these equations are obtained when we get data from experiments or when we do experiment in lab, and then we get some kind of graph. Then we do some curve fitting using MATLAB curve or using some other software. Then we can derive these equations from the results, but not derive using any physics like Newton's law and so on. So the constitutive equations are mathematical models of real behavior of materials that are validated using experimental results. So for example, in fluid mechanics, we have liquid and gas constitutive equations. So for example, in liquid, we can use Navier-Stokes equation, for example. And then for solid mechanics, we have some other materials like metal, fiber, reinforced composite, rubber, and ceramics. And all of these materials behave differently. So we cannot have one single model to describe the properties or the behavior of these materials. So we have model for metal, material model for composite, for rubber, and for ceramics. So because there are so many material models, so in this lecture, we will cover only two types of model, which is the common linear elastic model, and also I will introduce to you the hyperelastic model. So for linear elastic materials, so many solids such as metals, concrete, wood have the property that they undergo very small changes of shape when you subject to forces. So for example, metal, when you apply force, then it will extend a little bit or change in shape a little bit when you apply forces. So they also will sometimes return to its original shape when you remove the forces, provided that the forces are not too large. Okay. So the theory of linear elasticity provide an excellent model to describe these materials. Okay. So we can define a linear elastic material to be a material with internal energy per unit volume in reference configuration that has the following properties. So the internal energy is a function of components of infinitesimal strain tensor E and approximated by quadratic function. And the total kinetic energy plus internal energy equals the rate at which mechanical energy or mechanical work is done on the body. So we can define using W or the strain energy function. So the strain energy function for linear elastic material is 1/2 times C times infinitesimal strain E and times infinitesimal strain E. So this C here is known as the elastic constant. And why this IJKL here is basically represent the size of the matrix. So here the C, the constant C, is actually a 4x4 matrix or not. It's a 4-ordered matrix, okay? 4-ordered tensor, which has 81 components. So for linear elastic, if you still remember um, in your SOM or mechanics of material, we have this kind of graph, which is stress versus strain. And then we have a graph look like this, the linear region. And then after the material reach some point here, then it will start to form plastic deformation before it breaks. Okay. So linear material, basically a material that behave within this range here. Okay. So if you apply too much force on the material, then it will start to form, it will start to undergo plastic deformation, and then possibility of breaking. Okay. So basically the linearity here is also known as the Hooke's law. So just now we have the elastic constant that has 81 constant, 81 elements, but due to symmetries, and here I don't show you the derivation. So we can reduce the number of independent constant into 21. Then the elastic constant can relate the stress and strain using this formula: stress equals C times strain E. And this is the generalized form of Hooke's law. So this is basically the Hooke's law, which states that the stress is linearly related to the strain. Okay. And if you write in tensor form, you can write the formula in this form. So the matrix C here now reduced into a 6x6 matrix. So now we focus our linear elastic material into isotropic linear elastic materials only. So isotropic materials are those material that has mechanical properties independent of the direction. So for example, if you have plastic bottle, glass, diamond or metal, the properties of the material are the same in all direction. So what is this direction means? So for example, if you have wood, or if you have your table, if you can see on your table, the wood has some kind of macam urat kayu tu. Okay. So the urat kayu is going into one certain direction. Okay. Just like in this figure, the urat kayu going into some direction. So the properties of this material is different if you pull it along the urat kayu direction. But if you pull it perpendicular to the urat kayu, then they behave differently. Maybe dia senang senang koyak ke, berbanding tarik dia ikut arah urat kayu tu. So some other materials that we call anisotropic or not isotropic slate. I don't know what is slate, ice, and tourmaline. So this is another example to show to you what is the difference between anisotropic and isotropic material. So for isotropic material, the material behavior is the same throughout the materials. But for anisotropic, it will follow certain direction. Like for example, the random here is isotropic, while the other three figures or the three blocks here represent materials that are anisotropic or following certain direction. Sometimes in a material there are many directions or many urate, and we call it multi-directional material. So for isotropic materials, the stress-strain relationship can be expressed using this equation here. Or you can invert to find the strain in terms of stress. Okay. So here in this equation, we have V and E. So V is the Poisson ratio and E is the Young's modulus of that material. And the elastic constants, so this portion here is the elastic constant, C. So the elastic constant for isotropic material can be described using either two of the moduli, such as in previous slide, we use Poisson ratio and Young's modulus. But there are 5 moduli or 5 elastic constants that can be used to define the material behavior for isotropic linear elastic. So we have bulk modulus K, Lame's first constant lambda, shear modulus G. Sometimes we can use the symbol mu, and we have Poisson ratio V and Young's modulus E. So any two of these moduli can be used to calculate the elastic constant C, and this is shown in the following slide. So this table basically summarizes how we can use two moduli to obtain the other moduli. So for example, if you are given lambda and G, only lambda and G, then you can obtain K by using this formula. You can obtain E, you can obtain V, and there's another moduli M, which is seldomly used. So for example, if you are given G and V, or for example, in the previous slide, you are given E and V, so we can find K. E is already given. So lambda, we can find lambda, can find G, can find V. V is already given. So if you are given in your question or in your task, let's say uh, assignment or FYP, if you are given only two material properties, so in case you want to find the other material properties, you can just use this formula. But please remember, this is for isotropic linear elastic materials only. So if your material is not isotropic, then the formula will be slightly different, okay? But the conversion formula here is only for isotropic material. Now let's look at an example. So example 1, determine the stress tensor components at a point in 7075 T6 aluminum alloy. So this aluminum has E72 gigapascal and shear modulus 27 gigapascal. If the strain tensor at the point has the following components. So this is your strain tensor. So you are given E and G. So firstly, you are given E and G. So the formula given to you has only E and V. So E is already given. So you need to determine V. So to determine V, you just use the table and find the column that has E and G. So this is the E and G. And try to calculate V. So V is E over 2G minus 1. So use this formula to calculate V, and you get V equals 1 over 3. And then you can use E and V and substitute into this formula. So first determine C, the elastic constant. So you have determined E and V. So E is given and V you determine from the table. Substitute and you get the final elastic constant C. And then you can calculate the stress tensor using this formula or the formula from this slide. So firstly, what you need to do is you need to arrange your strain into a one dimensional array. So your strain just now is in 3 by 3 matrix. So you need to arrange them in a 1 by 6 matrix. So how to arrange them is just simply replacing these values here. So what is epsilon xx, yy, zz, and so on? It's just basically this strain tensor has this form. So xx is here, yy is here, and zz is here. And then this is xy, this is xz, yx, yz, zx, and zy. So you just convert from this in matrix 3 by 3 into matrix 6 by 1 matrix. Okay, after you arrange them, then you can calculate this. I think you have to calculate this manually one by one. Okay, so just darat silang lah. Okay, so when you multiply this, you will get the stress tensor equals this. Okay, so it's fairly straightforward, but you need to check what parameters you are given and then try to find the parameters that are not given to you from the table. Okay, so I leave it to you exercise 1 for you to try later when you want to study. Okay, so here in this exercise you are given lambda and mu, so you need to find E and V. All right, so that's the end for elastic materials. Now we look at hyperelastic materials. So hyperelastic material is also an elastic material in which the stress-strain relationship can be derived from strain energy density function. So for example of hyperelastic material is rubber or getah, where the stress-strain relationship is linear at a very small portion here, but after that it becomes non-linear. But the difference between hyperelastic material and elastic material is that when you release the force, let's say at this point, then the material will go back to its original shape, and it will take a lot of forces or stress to break the hyperelastic material. So if you have a stress strain curve, so linear elastic material maybe behave like this, but for hyperelastic material it will take a long time before it reach plastic deformation. So for example of hyperelastic material model are Neo-Hookean and also Moni-Rivlin material. So the hyperelastic model can be defined using strain energy density function similar to linear elastic material. But the strain energy density function can be defined in terms of the deformation gradient or F. This function can also be defined in terms of the invariance of Cauchy-Green deformation, which is C or B. So the invariance of C can be calculated using this formula here. Then we can relate the stress and strain for isotropic hyperelastic material. So again, we focus on isotropic hyperelastic material. So since the strain energy function W is in terms of deformation, then we can then find relationship between strain and stress for hyperelastic material. So for isotropic hyperelastic material, the stress can be obtained using second polar Kirchhoff stress tensor, which is given by this formula. So if C is defined in terms of invariance, let's say C is C I1, I2, and I3, then using chain rule, we can rederive the second polar Kirchhoff stress tensor as this. Okay. So this is the formula that you need to memorize, not memorize. You need to look for when doing the exam later. So for example, if you are given the strain energy for a vulcanized rubber, let's say this is the strain energy for a vulcanized rubber, where A, B, C are constants, then you are asked to determine the second polar Kirchhoff stress tensor. So basically, you want to determine this from this formula here. So what you need to do is you need to find all of this one by one before you can multiply them all together. So firstly, you find del W del I1 equals A, del W del I2, del W del I3, and so on. Okay, so make sure you know how to differentiate the equation correctly. Okay, so that's the only problem that you are going to have when finding these uh, differentiations. After you found all of them, then you can substitute into this formula, and then you get the final second polar Kirchhoff stress tensor equals this. And then let's say you are given another example. So let's say example 3. So from example 2, determine the relationship of the constants A, B, C if the material at zero strain has C equals I. So I is identity matrix. So at zero strain, we know that the stress also zero at zero strain. So this is another assumption. So firstly, you need to find the invariance at zero strain. So I1 just now equals trace of C. So C is identity matrix. And then the trace is basically you add up all the diagonal elements. So you get 3. And then I2 is this formula. So trace of C squared, you get 3 squared minus trace C squared. So if you square C, you still get identity matrix. So you still get 3 here. So you get this value. And then I3 is just determinant of C. You get 1. And then substitute all this into the previous relationship. So substitute, then you get this relationship here. And then because all of this depends on identity matrix I, then you can take any diagonal element of this calculation here. So you get 2 times A plus B times 3 minus 1. Simplify, you get A equals minus 2B. Okay, so again, this is quite straightforward. The only problem that you might encounter is to differentiate the equation correctly. Okay, so please differentiate it carefully so that you don't make some silly mistakes later. Okay, so I again leave it to you, exercise 2, for you to try later uh, at home. Okay. So that's it for today's lecture. And that's the end of our class. Okay. Basically, starting next week and week 14, we will have a talk. So please remember the talk is 5% each. Okay. So there are 2 talks, 5%. So please attend. There will be um, some form that you need to fill in, and additional marks will be given if you are asking question to the panel. Okay, so please try to ask question to the panel, because I will evaluate your involvement with the talk later. Okay, so I think that's it for today's class. And for final exam, I want you to discuss among your friend when you want to do your final exam. If you prefer to do it early, I'm fine. If you prefer to do it on the date allocated, I'm also okay. But I actually prefer to do it early so that I can enjoy my holiday as well. So that's it for today's class, and see you next week, inshallah. Assalamualaikum and goodbye.